In this video I'm going to talk about the central limit theorem, which is one of the most important concepts in statistics, and it's what allows you to make an inference from a sample to the population. The central limit theorem states that if we sample over and over again from the same population, the mean of the sample means will approximate the true mean of the population. Now, what does it mean when we're talking about the mean of the means? Let's try and illustrate it in an example. Imagine you want to find out what the average memory score of university students is. So you have your student population, all the possible students. But you can't measure every individual student. So you take samples from the population. You take several of these samples and you calculate the mean score. If you repeat this over and over again, you will find that the scores vary from each other. They're never quite the same. Some might vary more than others. So, for example, in the first sample you have 4.5, in the second sample you have 5.6, in the third sample you have 5.8, and in the fourth sample you have 3.9. So if you repeated this over and over again, you'll find that most of them will be somewhere around the true population mean, somewhere around 5. But some of the samples will be a lot higher or a lot lower. So if you'd repeated this several thousand times, and you then calculated the mean of the sample means, you would find that the number you get is a pretty good approximation of the true mean for the student population. This is because most of your sample means will be close to the true population mean, and very few of your sample means would either be much higher or much lower than the mean of the sample means. So in this picture here, we've plotted the distribution of the sample means if you sampled several thousand times. What you'll find is that most of your sample means will cluster around the centre, so around the mean of the mean. Here. Much fewer of your sample means will be at the extreme end. So there will be much fewer sample means of 9 and 10, and very few sample means of 1 and 2. This principle is why we can use a sample mean as an estimate of the true population mean. However, we can't really take thousands of samples, so we need to be able to determine how good an estimate any one sample is of the true population mean. And we do this by calculating the standard error. The standard error is the standard deviation of the sample means. So basically how far spread out the sample means are from the mean of the mean. And for any one particular sample, we can calculate or estimate the standard error by knowing the standard deviation of the sample, so how far the scores are spread out within the sample from the sample mean, and the sample size. And the formula for calculating the standard error is the standard deviation divided by the square root of the sample size. So if you have a sample of 40 people and the sample has a standard deviation of 4, you take 4 and divide it by the square root of 40. And what you can see from that is that the standard error will be larger if the standard deviation in our sample is larger, or if we have a very small sample size. Let's try and illustrate this with some graphical images. Imagine you take two samples. The red circle is your sample, the black dots are the individual scores in the sample, and the blue line is the mean score for that sample. So in both cases, for sample 1 and sample 2, you have a mean score of 4. But if you look at the dispersion of the data, of the individual points, they're much more spread out in sample 1 than they are in sample 2. This means that the standard deviation is going to be larger for sample 1 than it is for sample 2. So a mean of 4 in both cases, the same number of participants for each sample, but a standard deviation which is 3.6 in sample 1 and a standard deviation which is 1 for sample 2. This means that the standard error is going to be larger for sample 1 because we have the same sample size, but we have a larger standard deviation in sample 1. So how do we calculate the standard error? For sample 1, we have a mean score of 4. We have 3 individuals in the sample. We have a standard deviation of 3.6. So we take the standard deviation of 3.6 and we divide it by the square root of the sample size, which is the square root of 3. So we take 3.6 standard deviation, divide it by 1.73, the square root of 3, and we get 2.08. For sample 2, we have a mean memory score of 4. We have 3 cases and a standard deviation of 1. So we take the square root of 3, which is 1.73, and then we divide 1 by 1.73, and we get 0.58. So going back to the graphical images, you can see for sample 1, which has the largest standard deviation, the standard error is larger than in sample 2, which is the same sample size but has a smaller standard deviation. Let's have a look at another example. We have sample 3, which has 8 cases, mean of 4.5. Our sample 4 has the same mean of 4.5, but we only have 3 people. Now the standard deviation, the spread of the data from the mean, is fairly similar in both cases. 2.4 for sample 3, 2.5 for sample 4. So if we calculated the standard error, it would be much larger in sample 4 because the dispersion indicated by the standard deviation is similar for both samples, but the sample size is smaller in sample 4. So we have a larger standard error for sample 4. So if we look at the calculation, for sample 3 we have a mean memory score of 4.5, we have 8 people, a standard deviation of 2.4. So we take 2.4 and divide it by the square root of 8, the square root of the sample size, which is 2.83. And that gives us a standard error of 0.85. If we do the same calculation for sample 4, we have a mean memory score of 4.5, we have only 3 people, standard deviation of 2.5. So we take the standard deviation, 2.5, divided by the square root of the sample size, which is 1.73, and that gives us a standard error of 1.45. So this means that our sample 4 has a larger standard error because it has the smaller sample size. So if the standard deviation is similar, the standard error will be larger for the sample with the smaller sample size. So what this means is that the standard error is a function of both the sample size and the variance. And really, you want a smaller standard error, because the smaller the standard error is, the more likely it is that your sample mean is a true approximation of the population mean. So obviously sampling more people is easy, but how do we try and reduce the variance? How do we try and get a lower standard deviation? Well, the best way of doing this is ensuring that you have a very tightly controlled experiment so that there's less influence from extraneous variables that are not part of the experiment. For example, distracting noise. Imagine you're running a reaction time experiment and there is a lot of noise. The participant might be distracted at times and not respond. So your scores would be very, very variable. If you have a very tightly controlled experiment, the participant is not distracted, the scores are much likely to be less variable. and this ultimately results in a lower standard deviation. This way, by having a decent sample size and a relatively low variance, you can be sure that your sample mean is more likely to be a good approximation of the true population mean.